going to take a look at the fundamental counting principle and permutations. So in this video, we're going to be able to understand what the principle is, how to calculate it, and then we're going to look at permutations of objects. So the fundamental counting principle is a little misleading in the name. We're not actually counting things up as in counting 1, 2, 3, 4. What we're doing is trying to figure out what the total number of options are for complex situations. So for instance, if I am trying to find the number of outfits that could be made with different shirts and shoes, the principle gives us a shortcut to actually matching those up and counting them on a factor tree. So what does it even look like? So let's go back to our blood type example. In the blood type example, there's also a factor that's denoted with a plus or a minus. And if a local blood bank labels those donations according to the plus and minus and gender, how many different ways could a blood sample be labeled? So let's think about this. There are 4 possible blood types, 2 for the RH factor, meaning positive or negative. So I have 2 possibilities for RH, and for 2 possibilities for gender. We're just going to simplify it for that. So if I want to actually use the fundamental counting principle, I would do 4 times 2 times 2, so the number of options for my blood type, times the number of options for the RH factor, times the number of options for gender, and so I get 16 different ways. So that saved me the time of actually writing AB plus, AB minus, O plus, O minus, and so on, and then actually having to physically count. Another example would be in, if I'm thinking about repeating things, let's say I have 5 letters, and they're used in a 4-letter ID card. So think about it like an address or an ID number. How many different cards are possible if letters are allowed to be repeated? This is an interesting problem. So if I can repeat letters, I have 5 letters that could go into each slot. So I would have 5 times 5 options times 5 options times 5, which is 625 options. This is why the principle of counting is so important, because you wouldn't want to come up with all the possible combinations of those 5 letters. It would take you all day. In part B, they say I can't repeat the letters, which means once the letter A is used, it can no longer be used in the other 4 places for the ID. So that means my first slot, there's 5 letters I can choose from, but in my second slot, I can't reuse the letter that was picked for the first slot. That means there are 4 options. And then the next one would have 3 because I can't repeat the previous 2 letters. And then the last one would have 2 options. So that's still 120 different ID numbers or ID codes. So one of the interesting things that we do is instead of writing 5 times 4 times 3 times 2 times 1, we use a factorial. So a factorial literally means count backwards. So 2 factorial, if I count backwards, would be 2 and 1, and I would multiply what I'm counting backwards with. So 3 factorial, count backwards, 3, 2, 1, and then multiply those numbers. So if I'm working with factorial notation, this is the actual mathematical explanation. We're not really going to see this a lot in ALEKS, but it is important to be exposed to it. So if I do have n factorial, it's read n factorial. So an exclamation point is read as n factorial in math. What's interesting is that 0 factorial is actually equal to 1. And that's where a lot of students will get tripped up in ALEKS, is because 0 factorial is 1 and not 0, like our instincts tell us. Some of the formulas we're going to be working with throughout probability will use factorials. And so it's really important that we understand the rules that apply to a factorial. So if I have something like 3 factorial divided by 3 factorial, that follows traditional rules, and that's going to be 1 because you have the same thing divided by itself. And the nice thing is factorials are a shorthand. So if you wanted to write 5 factorial, you don't have to write 5 times 4 times 3 times 2 times 1. So it's kind of a way of shorthand, like scientific notation. So let's practice with factorials. So in the first one, if I want to evaluate 8 factorial, evaluate means actually find the number. So 8 factorial, I'm going to count backwards and then multiply those out, and that gives me 40,320. In part B, for 12 factorial, I'm going to count backwards and then multiply those out, and that would be what would give me the number. But what's interesting in part B is it's actually 12 factorial divided by 10 factorial. So we could think about that as 12 times 11, but instead of writing 10 times 9 times 8 and so on, I could say that that's actually 10 factorial, and I could cancel out the 10 factorials. So when you have a smaller factorial in the denominator, you want to stop once you've reached that number counting backwards and then cancel out. And I'm left with 12 times 11, which is 132. In part C, I already know that 12 divided by 10 in the factorial is 132. And on the other hand, if I think about 6 factorial divided by 5 factorial, there's no way that that's going to be equal because I'm not multiplying the same things. So when dividing 2 factorials, you can't ignore the factorial and just say that 6 divided by 5 reduces to something else. So 12 factorial over 10 factorial does not follow fraction reduction rules. It is not equal to 6 factorial divided by 5 factorial. So the big takeaway here is you cannot reduce fractions with factorials in them. Permutations are an arrangement of the number of objects. If you think about how many ways can I arrange the, ceramic pieces on my mantle, that would be a permutation. So how many ways can you arrange a bunch of objects? In permutations, there's going to be a shortcut, but if I'm thinking about what am I actually doing, I can use this example as a kind of a launching point to understand the thought. So let's suppose that a photographer wants to arrange 3 people, Carmen, Juan, and Christina, in order for a picture. So if I listed the possible orders, then that's going to be these pieces. So I'd actually manually wrote out all the possible ways to arrange the 3 people. And I count them up, and there's 6 total possibilities. In part B, if I'm using this principle, I think about it and I say, well, there's 3 ways that we could choose the order people go in, because I have the first person, the second person, and the third person. So I'm thinking it more abstract and not about the specific people, but how many slots are there? There are 3 slots for people. So if I do that, then that's a factorial. So I have 3 people in the first slot. I can't use that same person again, so 2 people in the second slot, and then 1 person, which actually gives me 6. And that's what I got when I wrote it out, so I have verified my work. If there were 8 people in this portrait, it gets really complicated because instead of 3 slots, I now have 8 slots. And so I would not want to write out the number of ways that I could put 8 people into this photo, because that would be 8 factorial, which is 40,320 ways. So the moral of the story is the counting principle really simplifies and shortens the work that you're doing to come up with a final answer. And it's very critical that you use it and you understand it so that you can save yourself a lot of time and grief. So if I want to make a conclusion here, I can say the number of ways I can arrange something is going to be the number of slots I have factorial. So let's revisit another example. There are 7 horses in a race. If you win the race, you get a big jackpot. And so you have to pick the finishing order of all 7 horses, and then you're able to get a jackpot yourself. So if we think about how difficult would it be to actually do that, to actually guess all 7 places correctly. And so when I do that math and I look at that, then I can see that I have 7 slots to guess, which really gets very creative in how to do that. So if I have 7 slots to guess, then that means that I'm going to have a lot of opportunities, 7 factorials. There are 5,040 ways to finish those orders, which is pretty complex. How many different ways in this example can a pledge class with 20 members choose a president, a vice president, and a Greek council representative? So this is that same problem, but I'm just simplifying how I'm looking at it. So I don't have 7 slots. I'm going to have 20 slots, but 20 people, but I'm only going to have 3 slots. So if I do that, I have 3 slots. So the first person, there are 20 options for. But the president cannot be the president and the vice president, which means that the second slot only has 19 possibilities, and the third one only has 18. So I get 20 times 19 times 18, which is 6,840 different ways. That's a lot to assign those 3 offices. So again, that would be very difficult to do if you were actually writing all of those out. So let's formalize what we're doing here. So if I'm just arranging objects, that's a factorial. If I'm wanting to look at selecting a number of objects out of a pool like I just did, then I could use the permutation formula. And so the permutation formula is in your calculator. If you use Web 2.0 or another calculator, you can find it in there. It's Npr, so you don't have to actually use the factorials. You'll use Npr. So if we think about this, let's solve a permutation problem. So in a lottery game, there are 40 numbered ping pong balls that are put in a bin, and they choose 4 at random. To win the game, players need to win all 4 for which they're drawn. How many different winning orders are there? So this is a permutation because I'm choosing 4 balls out of 40, and there's no repetition. We can't have repetition. So what that means is if I'm using 4 balls out of 40, if I use the permutation formula, that's going to remove all those redundancies where something could be just selected in a different order. So like red, blue, is not the same as blue, red. Even though they have 2 blues and 2 reds, I have to eliminate all of those extras to get Y. So when I use the NPR formula, I have 40 total. I'm selecting 4. So that would be 40 choose 4, which you can plug into the formula here, or in your calculator, you are able to utilize it as, and I'm just going to shift over to the Web 2.0 calculator. You are able to utilize that as NPR. So if I do NPR, and I have 40 items, I'm choosing 4, you get the same number that you got here. So you need to make sure that you hit NPR first. Get back to that window. So I hit NPR in Web 2.0. I do 40, 4, and then I select, and that gives me my answer. Now, Web 2.0 is a free online calculator. If you Google Web 2.0, you'll be able to find it and use it for this assignment. So if I'm looking at permutations with objects that are alike, there's a slightly different way that I have to do it. So if we think about how many different passwords could be used using all the letters in Mississippi, that means I have the same number of slots there. That means the letters could be arranged. I have 1 M, I have 4 I's, 4 S's, and 2 P's. So utilizing that new formula, I have 11 slots Mississippi, and then I'm going to divide by 1, 4, 4, and 2, which is coming from this section. and that's the number of unique passwords that I can get.